Yeah, so you've already seen one exponential plot so far. All the usage of AI is becoming exponential, or in demand for tokens. And another way to visualize it is the utilization of energy. And so this is a quick statistic from the Department of Energy showing that when we just had CPU data centers deploying the web, essentially, we spent about 60 terawatt hours in the US of energy to power those data centers. With AI, that is predicted to grow tenfold to about 500 terawatt hours, and I think that's a conservative prediction. And so the demand for AI efficiency, as we've heard before in Natalie's talk, is very high, and that's the problem that Makora is trying to solve. This is a quick snapshot of what the AI software stack looks at with large blocks, essentially. We start by some of these models, some of these software agents, Cloud Code, OpenClaw, some of other autonomous agents, theorem-proving agents, and other things. And then you go through this somewhat complex software stack before you hit the hardware layer. And so performance engineering in this software stack is what dictates performance. You've also heard that GPUs are utilized about 20 to 30%. It's because this software stack is difficult and inefficient. And just to highlight kind of the difference between an efficient version of deploying that software and an inefficient one, not picking on any specific cloud here, but this is an example of what we can achieve on Kimi K2.6, a frontier kind of open source coding model, and what one of the existing cloud providers can do if we benchmark their existing endpoint that they serve to customers today. So you can get a 5x improvement just from the software alone by optimizing that software. And I'll talk a bit about what we do there and how we achieve that kind of performance. And yeah, looking at it another way, if we benchmark against kind of the best artificial analysis, which is an independent benchmarking kind of organization, we can kind of match the performance of the best optimized model on this specific plot. So stay tuned for another one of those plots later. So you might be asking now, why is this difficult? Why is it so hard? Why don't we just write that software and make sure it works great all the time? And it's difficult for many reasons. The first one, starting from much closer to the GPUs, the GPU code is actually very hard to write. I can name maybe a few people that can do that in my own circles. Maybe there are tens, hundreds, or thousands worldwide that can write very efficient GPU code, and it's genuinely difficult to write. The most important chip in the world right now is the Blackwell B200 and the other B300 chips from NVIDIA. They're running most of AI in the world today. And they have the only way to access their matrix multiply instructions and get the most efficiency out of them is an instruction called TC-Gen05. It's the 5th generation of tensor cores. And this instruction is promised to not be forward compatible. It won't be compatible with the next version. It's not backward compatible. In fact, the instructions used in the previous generation of GPUs can only access about 25% performance on Blackwell GPUs. And so every time a new GPU or a new AI chip comes out, the hardware cycle has become so fast, every year we have a new chip, that there is no time to build software abstractions. The AI hardware companies are just trying to expose performance at any primitive level, in this case, almost assembly-like level, PTX, and giving it to the developers to try to write their kernels. And so one of the most important kernel just means GPU function, out there is flash attention. And from the release of Blackwell until flash attention was implemented, it took about 9 months. I was talking with clouds who were saying, I wish I bought more of the previous generation GPU because that's what everyone is asking for. We can't use the Blackwell chips yet. This is now history though. So what Makora does, so what my company does, is that we're trying to automate performance engineering, starting from this kind of GPU kernel generation or GPU kernel writing side. Our first product is called Makora Generate. It automatically writes that GPU code for you. You can probably guess how. It's using agents to do that with a very tight evaluation and profiling loop. We've also worked with OpenAI to fine-tune their frontier GPT models. I believe at the time we were like one of 2 companies who were able to do that. And we were actually able to push the frontier of the best models out there in generating code for GPUs. Using our kind of curated data set. We were so successful at it that we were able to sell that data set to other frontier AI labs. We also bootstrap our kind of generation tool with expert written snippets. So we have very kind of detailed steering for these tools, and we keep adding to this database. We kind of have 3 tiers of memory, like short-term memory that the agent writes as they go along, longer-term memory that's written by experts, and even bigger kind of open-ended web search kind of memory. And our tool is kind of in 3 form factors. We have it, command line, pip install Macora on the web, and integration with, your favorite editor, which is probably Cloud Code. And so we support one extra thing that we're really keen on is to support all sorts of different hardware. So we have, of course, support for NVIDIA hardware, but also for NVIDIA, AMD. We're adding support for TPUs now, and all sorts of different programming languages. Here's a quick snapshot of results, being an academic and everything. And so we benchmarked against all of the kind of frontier models in this GPT-5 fine-tuning paper. And you can see here that on a standard benchmark of kernel generation problems for NVIDIA GPUs, with a top bar on functionality faster than PyTorch. So what percent of the kernels that we generate are faster than PyTorch? This is the second plot. And how much it's faster, about 2x, 2.12x in this case. We outperform kind of all existing solutions. And I show some customer success stories with some non-GPU examples here for Macora Generate. Okay, moving one layer up the stack, beyond kind of the GPU kernel code, we find the serving engines. And so these serving engines kind of aggregate user requests and deploy them onto the hardware. And here, the main issue is that this is a massive design space. There are multiple types of open source and closed source inference servers, and it's very hard to navigate that space. We've heard of some enterprises that are basically 10x less efficient than they could be because they don't have that performance engineering expertise. This is, again, the same plot that Natalie showed. Performance engineers live and die by this plot. On the x-axis is interactivity, so that's how fast each user gets their response. And then the y-axis is kind of efficiency, how many tokens I can push through one GPU, typically kind of inverse relationship there. But what I'm trying to highlight here more is that there's a huge design space. So these are all the Pareto optimal points on different kind of hardware setups. And so if you're a company deciding what hardware to buy, what software to use to deploy on that hardware, you have to navigate that space to find the best performance or cost. And here is kind of a news piece from Business Insider talking about Bank of America buying a bunch of B200 GPUs and likening it to a local car mechanic trying to drive a Formula One car or a race car or something. Like basically, normal people can't do this performance engineering, and you can see here a gap between using 44 B200 GPUs and 4 B200 GPUs to deploy the same model. We can get faster performance just using 4 GPUs. So that brings us to our second product, Macora Optimize, which is essentially inference server auto-tuning. We support kind of multiple types of inference servers. We choose the best one, we tune its hyperparameters, and customize it to the workload from up top and the hardware on the bottom to get the most performance out of it. So obviously we support, speculative decoding, newer versions of it, different kinds of quantization, and it plugs into Macora Generate by swapping in the fastest kernel for that workload and for kind of the traffic pattern as well to make sure we squeeze all the performance out of the software stack. We're also experimenting with completely bespoke inference servers that take a model and write like a customized version of that inference server and like just using code generation, obviously, to squeeze out even more performance. Yeah, here's a quick snapshot of a result. This is not, from one of the enterprises, but compared to an AMD optimized baseline by the company itself, we were able to even push that beyond the most performance solution from them by about 40% in performance. Okay, and then the next layer that I want to talk about is algorithmic optimizations. And so I talked about kind of low-level software, inference servers, but what is the actual inference algorithm that you're running on that chip? And there's a lot of room for improvement there. There are new papers that are coming out every day. And the idea is that because we have this automated software stack, we can adopt and deploy these ideas very quickly. We also have some ideas of our own. And so this is one of those ideas that I want to highlight that we have recently published called SMC-SD. So we develop a new algorithm for fast inference. I won't go through the details, but I'll point you to the paper. But if we go back to this artificial analysis plot, this time it's Llama 70B. Here we can see that kind of the fastest GPU-based solution comes from this company. It's about 130 tokens per second. And then Grok, which is a company that builds their own AI chip, recently acquired by NVIDIA because they can unlock kind of the super low latency. They were able to achieve, 308 tokens per second using 500 of those chips. So that's kind of new capability, very low latency, super useful for agents that kind of need to talk to each other and you want to get a response much faster. Just with our algorithmic change, we're able to outperform the Grok chips and get up to 342 tokens per second on just 4 H100 GPUs. So that's a lagging node GPU. Of course, there are footnotes to this result, but this is kind of new capabilities that we're able to do with these algorithms that we're also looking into and hoping to adopt quickly into our product as well. So looking again at this AI deployment stack, Mokora is about automating performance engineering throughout the stack. We started, Mokora Generate does it for kernels, Mokora Optimize does it for the inference server layer, and it all culminates in this Mokora Inference product, which we're hopefully releasing this week or very early next week. The idea is that, if you want to showcase performance, you have to show it in the end-to-end token per second performance. Some of our customers actually said, this is amazing, you should actually sell tokens yourself, and we're going to start to do that. But we're also talking with enterprises to basically sell them the Mokora Optimize and Mokora Generate parts of our software stack so that they can deploy models of their own internally. So we have kind of in talks with, various enterprises for that layer and for hardware companies as well in the Mokora Generate layer. And we are telling them the same thing, just expose, APIs to access performance in your chip, and we'll make sure our code generation gets you the best performance out of it. This is a quick preview of our kind of deployment engine. It's about to be released, as I said, and you can see on the tab here, we have, inference, optimize, and kernels, and we're going to keep adding build tools and deployment tools to that to be kind of a one-stop shop for all of AI performance engineering. This is our team. You can find our CEO somewhere. He's probably the only one in shorts, and this you have been around for a year and a half, raised the seed round. Thank you for paying attention. Thanks.